titrations come up twice during the course of the AP Chem curriculum. Once now focusing a little bit more on the stoichiometry of an acid-base reaction, and then second semester we do a whole unit on acids and bases, and then we focus a little bit more on the molecular structures, what's changing, and all that good stuff. The last couple calculations that we've done could be considered titration calculations. It's when you're joining an acid and a base, sometimes you're trying to find the concentration of an unknown acid or base, which is probably the most common type of acid-base calculation. The setup for a titration is exactly what you did, hopefully you did, in a first year class, where you've got this big burette set up, there's a flask underneath, you've got two solutions. Usually there's one of known concentration, and the other one is your unknown. The known solution always goes in the burette. You're going to deliver the known solution, called the titrant. You deliver that to the flask containing the unknown, or the analyte, the solution that you want to analyze. You want to find the concentration of the unknown. So you got your setup, and we can mark that in here, that my known solution, my known concentration, that's always in the burette. And then my solution of unknown is in the flask. Okay, so you're going to mix the two together. You're measuring the volume of the known solution delivered to the unknown solution until you hit this equivalence point. This point where you magically have added equal moles of acid and base according to the ratio in the balanced equation. So the moles of acid and base will match the mole ratio from the balanced equation, which is why it's usually step number one. If we're doing any kind of titration calculation, we want to know the balanced equation. It's often 1-to-1 ratios, but it doesn't have to be. Now, realistically, how do you know in the lab when you've hit this equivalence point? How do I know when I've got equal amounts of acid and base according to the balanced equation? We use an indicator. And this indicator thing we'll focus on a little bit more second semester, like how to choose an appropriate indicator for different types of titrations. But you probably did this last year in first year chem. You added some kind of an indicator to the flask. And we look for a color change. Like, you know, maybe I had a strong acid and a strong base, and when I had equal moles of acid and base, it was supposed to be 100% neutral. So I looked for an indicator that would change color around a pH of 7. So we can kind of choose different indicators depending on what type of a titration we're doing. That we'll look at more second semester. Now here's just kind of the general setup of a titration, and we will do one in chapter 4, and then we'll do a bunch more at the end of the year. So I'd add the indicator to the flask, and then we add the two solutions until we see the indicator turn color, and that's when we should be at the equivalence point. Now I know this is kind of confusing. When the indicator turns color, we call that the end point. That's the end of our titration, signaling that we are at the equivalence point, where we have reached the ratio from the balanced equation. Now, again, those last couple of types of problems that we had done, those are pretty typical solution stoichiometry with acids and bases. That's all a titration is. It's just adding acid and base until you get this ratio from the balanced equation. It's just some stoichiometry. But I like this problem because this has come up on AP tests quite often, and it really throws kids off because they see all this stuff going on, lots of numbers, lots of compounds, and they just kind of give up on it. And it's actually a really simple problem. We have a chemist that is analyzing the effluent, which is kind of a waste material from an industrial process known to produce the compounds carbon tetrachloride and benzoic acid. So this waste material is a mixture of carbon tetrachloride and benzoic. It says that benzoic is a weak acid with one acidic hydrogen atom. I'm assuming that's supposed to say per molecule. Okay, that's going to be important. This one acidic hydrogen. It's actually this guy right here. It's a weak acid. It doesn't extensively ionize. But if it does, it'll only give off one hydrogen, just that first guy. A sample of this effluent weighing about 0.3518 grams was shaken with water. The resulting solution required, so about 10.5 milliliters of 0.1546 molar sodium hydroxide to neutralize. So here's what we got. They took this waste mixture, dissolved it in some water, and then they titrated it with a known solution of sodium hydroxide. Okay, and so we know the amount of sodium hydroxide required to neutralize the acid in that mixture. The sodium hydroxide is not going to react with the carbon tetrachloride, but it would neutralize that benzoic acid. So we can use this information to figure out how much benzoic acid was in that original mixture, and then we can calculate the percent benzoic in the original mixture. So let's start with the known solution. When you have a titration, you'll always know the molarity of one, and you'll also know the amount of that known solution that you used. So we've got 0.1546 molar sodium hydroxide. It equals moles per volume, 0.01059 liters. Okay, so if we cross multiply, we're going to get 0.001637 moles of sodium hydroxide. It's thinking about it. Sodium hydroxide. There we go. Okay, now I didn't write a balanced equation, which is kind of a no-no. But here's the deal. We've got this sodium hydroxide, which is +1, -1. And then we've got the benzoic acid, and it tells me that there's one acidic hydrogen. This kind of hints that it's going to be a 1-to-1 ratio. So if I wrote the formula equation, it would be this benzoic acid plus the sodium hydroxide. I would do like a double replacement, and I would end up with sodium benzoate. This is the benzoate ion, and then I'd have water, hydrogen hydroxide. Now, tricky, they don't ask for this, but they do tell me that this is a weak acid. Sodium hydroxide is a strong base. So if for some reason I was asked to put this as a net ionic equation, I do not get to extensively ionize this weak acid. That's going to stay. Then I would split the sodium hydroxide. That's a strong base. Anything with sodium is aqueous. And on the product side, the sodium benzoate is also a strong electrolyte. Anything with sodium will extensively ionize. And then I do not get to split water. Water is a liquid. So if by chance you were asked to scale this down to net ionic, the only spectator would be the sodium. And you'd have the benzoic acid reacting with the hydroxide. You'd have the benzoate ion and the water formed as products. Now again, they don't ask for any of that, but we'll just put it in there as another example of a net ionic involving a weak acid. Really, all I need to know is that it's a 1-to-1 ratio. So that's why I kind of like that they hinted that it has one acidic hydrogen atom per molecule. Cool. So here's what I like about that. If it's a 1-to-1 ratio and I know the amount of base, that must be the amount of acid. So if I had 0.001637 moles of sodium hydroxide, and I'm at this equivalence point, or it's neutral in my titration, that means I must be at the ratio of the balanced equation, which is 1 to 1. So I would have had the exact same amount in moles of the acid. So I'm going to make myself a little note. I can do this because it's a 1 to 1 ratio in the balanced equation. Okay, so now from here, often we get like the moles of the unknown solution. We know maybe a volume, and we have to find the molarity. This time, I want to calculate a mass percent. So I know the mass of the mixture. That effluent sample had a mass of 0.3518 grams. Well, here's the amount of acid that must have been in that sample. We just need to get that back into grams. So let's just do a quick switch. Cancel moles, put it in grams. On the periodic table, this is maybe about 122.12 for 1 mole. Now I do get to leave 4 sig figs. So this is kind of weird. 9. And there's grams of this acid. O2, benzoic acid. Don't round that to 0.2 because we get 4 sig figs. Alright, so now I can do this percent composition. The mixture had 0.1999 grams of acid, C7H5O2, and the total mass was 0.351, I think 18. Yep, 18 grams total. Now this is kind of weird, but when you do a percent on the AP test, they do want you to say times 100. It seemed kind of obvious, like, you know, plug in your calculator and just record it as a percentage, but they do want you to say times 100. And if we go 4 sig figs, I'm going to say 56 in a second. 56.82%. 82% acid. So it's kind of a titration problem, but in the end, when we get moles of this acid, we're going to turn it back into grams instead of like figuring out its molarity. And then we just do percent of the mixture. So it's not a crazy problem, but sometimes people get their undies in a bundle when they see too much information. But this one's actually pretty manageable.